Having seen how to derive the value of transforms of various common functions, it turns out we don't actually do that very often in practice. Well, why? Because once you've done the transform once, it's always going to be the same. If we examine the function 1 and we run it through that integral from 0 to infinity of e to the minus st times f of t dt, we're always going to get 1 over s. When we do the exponential e to the something t, we're always going to get 1 over s minus that coefficient of the exponent. When we do sine of kt, we're going to get k over s squared plus k squared. And so what this lets us do is very quickly jump into the transformed version without actually going through the definition of the transform every time. This is always under the surface. It's always available if we have a new function we might not have seen before. But for these functions that we know we're going to be using in our solutions, the transform becomes very simple to execute. Now, the transforms themselves wouldn't be that helpful unless we had this other important property. The transform is linear. For example, if we wanted to take the function 5 times 1 and find its Laplace transform, what we'd have to do, going by the definition, is integrate from 0 to infinity e to the minus st times 5 dt, but that's a constant. Any multiplying constant can be brought out front, and if we do that, we end up with the same integral we had before, e to the minus st times 1, and we already know what that is. It's in our table. It's 1 over s. So any multiplier by a constant, has to be constant, can be brought out front, and so we just get the constant times what we would have gotten for the transform of the simple function. More technically, for the definition of a linear transform, if we have any constant multiplier, a or b here, and two functions f and g of t, we can bring the a out front, we can bring the b out front, and if it's a sum, not a product, but a sum, then we can individually separate and calculate the integrals on their own, just like we would if it was a regular integral. So what we get if we're asked to transform a linear combination of two functions is simply the transform of each function by itself and whatever coefficients out front multiply afterwards. Here we're asked to take the transform of a linear combination of functions that we've seen before, and particularly functions that are in the table of transformations. Knowing that the transform is linear, this becomes straightforward. Let's take a look first at the cos 2t, cos of kt, so this is k equals 2. We also have the same thing here. When we're asked to transform sine of 2t, we have sine of kt is in our table. And the last but not least, a power of t, we have t cubed here, and this is t to the n in general. So that would be the n equals 3 case. What do we get with that transform? Then we can simply go down the line. We have the 4. 4 gets copied. The transform of cos 2t is the transform given in the table here. It's going to be s over s squared plus the k squared. And in this case here, the multiplier k is 2, so we'll have 2 squared. Then we'll have negative 6 times the transform of the sine of 2t. Again, the sine transform will be k now is in the numerator for this transform. And we also have an s squared plus k squared. Well, that's 2 squared here. And last but not least, we'll have minus 5, the transform of t cubed. This is a little more exotic, but we're using n equals 3. We'll have 3. Remember that this n to the exclamation mark here indicates a factorial, or n factorial overall. And we'll have that divided by s to the n plus 1, so s to the power 4. And we'll tidy that up maybe a little bit. Call it 4s over s squared plus 4 minus 12 over s squared plus 4 minus, this is 6, so minus 30 over s to the power of 4. And that would be the transformed version of our series of functions here with a linear combination. As another example, we'll find the transform of this linear combination of core functions. expressing it with the notation we've used now, the Laplace transform of 11 plus 5e to the 4t minus 6 sine of 2t's. We would look at this function here. It's 11 times 1. So it'll be 11 times the transform of 1, which would be 1 over s. We'll have plus 5 times the transform of e to the 4t. The transform of e to the 4t is 1 over s minus 4. The 4 goes in as the subtraction in the denominator. And then we get minus 6, the transform of sine 2t. Sine of kt is transformed 2, or the k, over s squared plus the k again squared. And again, we can tidy that up. That'd be 11 over s plus 5. I'll try to make my 5s and s's look different. Minus 12 over s squared plus 4. And so we discover that transforming functions that have been pre-computed or whose transforms have been pre-computed is a fairly straightforward process. There are some wrinkles that will come up, but if this process is making sense so far, then you're off to a good start.